welcome to this video in the Kinetics and Equilibrium chapter. This is 14.3, Ksp Solubility Products. Yes, it is another K. Right off the heels of the equilibrium constant for chemical equilibrium, today we are going to be hitting the equilibrium constant for solution equilibrium. So in order to effectively learn this lesson, you guys are going to need to have handy and printed your companion worksheet. You are going to need to have your plan sheet in order to try the homework questions. And of course, since there's calculations, you don't need an abacus, you need your calculator. So without any further ado, let's get started. So before we dive into KSP, we have to think about what we already know about solutions. So let's rewind and go back to Unit 13, which is the solutions chapter. If you recall, that chapter really talked a lot about what happens when you drop an ionic solid in a solvent like water. That solute will dissociate, which means the positive and negative ions in the lattice get pulled apart by the polar water molecules and they become hydrated. If you did have a polyatomic ion there, that would also get pulled apart, but the actual ion itself would stay intact, and that was all part of solvation. What else do we remember? Well, we worked with this thing over here. This is our table G. These are our solubility curves. And if you recall, solvent solutions do have a maximum amount of solute that they can dissolve. And obviously, we see here that's affected by temperature. But for all these salts that we see, solubility varies. We also learned that there are many ionic salts that don't dissolve. For instance, we have halides and sulfates that are usually very soluble, except when they are combined with this. We said that they were insoluble, and obviously on this table here we have all the insoluble salts and obviously the exceptions. Well, today I am here to tell you that that table may have been a little white lie, because things that are said to be insoluble actually are soluble to some degree. So the first thing you guys should write down in your notes is that all ionic salts do dissolve to some degree. The ones that we said were insoluble actually were not very soluble at all comparatively to the salts that table F previously said are soluble. If we take a closer look at what was old reference table M, we can see down here all the KSP values for different salts that were previously on table F. By looking at this, this works just like the equilibrium constant for chemical equilibrium did. The value matters. When it's greater than 1, it favors the products. When it is less than 1, it favors the reactants. So look at silver bromide here. You can see that this value is a 5.0 times 10 to the minus 13. That means overwhelmingly the reactants are favored, which means it does not dissociate into that many products. So at equilibrium, our saturated solution, we are favoring our reactants. And you could get down to here that at least lithium carbonate is somewhat soluble, though previously on table F we said it was insoluble. Its KSP value is 2.5 times 10 to the minus 2. This is a little bit, well, a lot of it closer to 1 in terms of the value of its equilibrium constant. So in order to get to the end, which is doing the KSP calculations, we have to be able to write the equilibrium constant for a solution. So in order to do that, here is an example. It all starts with the dissociation equation. So take your salt and write the dissociation equation as you would have in chapter 13. We did that here for you for silver chloride. Remember, it breaks up into its component ions that are there. So pause the video now and make sure you are able to effectively write dissociation equations. Otherwise, that's probably a spot where you'll get stuck. Pause the video now and then unpause when you are ready for the answers. All right, if you did this correctly, you will have gotten what we see here. A couple things to make note of. Remember, when you're writing a dissociation equation, the subscript turns into a coefficient. So when lead to bromide dissociates, there are twice the number of bromide ions as we have lead ions, and that's going to be important for the math later on. What we also need to be able to do now is take that dissociation equation we wrote and write the equilibrium expression for our salt that's dissolving. So again, we're going to use silver chloride here. Here's our dissociation equation. If you recall from an earlier lesson that we did on the equilibrium constant, we write that by taking the concentration of our products and we raise them to a power of the coefficient in the balanced equation and we put it over the concentration of our reactants. So in the event you do have coefficients, remember, make them your exponents. The other thing you have to remember is that you need to omit solids and liquids from your equilibrium expression and only include aqueous and gases, as those are the things that actually will achieve an equilibrium. So if I wanted to write the equilibrium constant for this equation, it would look like so. Okay, your turn. Pause the video now and write the equilibrium expression for these salts. Remember, you have to begin by writing the dissociation equation first in order to figure out what it breaks up into. Pause the video now and then unpause it when you're ready for the answer. All right, if you did it correctly, here are your equilibrium expressions for these equations. All right, let's get into the mathematics of these KSP calculations, and it will require you to carefully read the questions. So our first example says we have a saturated solution of barium sulfate, and one of the ions, the barium ions that we see here, actually has a concentration of 3.9 times 10 to the minus 5. So that is of the barium ions. So if this is 3.9 times 10 to the minus 5, I can now infer that the sulfate ion is also 3.9 times 10 to the minus 5 molar. Now, why is that? Well, when barium sulfate dissociates, every one barium sulfate winds up breaking up into one barium and one sulfate ion. So we have a 1-to-1 ratio here. So the concentration of one ion is going to be equal to the concentration of the next. To move on with that calculation, right, now we know Ksp is equal to the barium concentration times the sulfate concentration. So now we're just going to substitute in. If I see my Ksp is equal to 3.9 times 10 to the minus 5 times 3.9 times 10 to the minus 5, or squared, I wind up getting a Ksp value of 1.5 times 10 to the minus 9. So really not that hard at all. So let's jump into our second example, which is a little bit more difficult than the first, and we have to make some considerations. Let's check out the dissociation equation. You'll notice that here we have a salt that when it dissociates, it is not like the example that we just did on the previous slide. This one is actually going to break up in a 1-to-2 ratio. Every one lead-2 fluoride here is going to beget one ion of lead and 2 of fluorine. So that is going to mean something for our concentration. They're telling me in my question here that the concentration of the lead is 1.9 times 10 to the minus 3 molar. So this concentration is going to need to be twice that, and we're going to talk about that in a second. So let's write our Ksp so we know what we're doing. We know that Ksp is equal to the lead-2 concentration times the fluoride concentration. And of course, because we have a coefficient of 2 here, we have to raise that to the second power. When we go to math this out and throw some variables in here, we're going to use x's, we know that Ksp is going to be equal to x times, now remember this, the fluoride ion was going to be twice the concentration of this, so we are going to get 2x raised to the second power. So remember, the molarity would not be 1.9 times 10 to the minus 3. It would be twice that, which would be 3.8 times 10 to the minus 3. So that will show its head in our calculation. So if I was going to do this step by step, I would say that Ksp is going to be equal to 1.9 times 10 to the minus 3, and we'll put that in brackets, times 2 times, in parentheses, 1.9 times 10 to the minus 3, and we're going to raise that to the second power. That gives me Ksp is equal to 1.9 times 10 to the minus 3 times 3.8 times 10 to the minus 3 squared. And that is going to eventually give me a Ksp, I'm going to put it in my calculator, of 2.7 times 10 to the minus 8. So really not that bad when you consider everything that we had to do for this problem to get an answer. So when we want to make meaning of our KSPs, like we said before, the higher the KSP value, the more soluble your salt will be, the more ions it'll produce in solution. The smaller, the less soluble, and the less ions. Thinking about it in terms of equilibrium, the larger the value, the more it favors your products. The smaller the value, the more it favors the reactants. If you do have a large KSP and you have an ionic solution, your level of conductivity is much greater. Why? More dissolved mobile ions means greater electrical conductivity. So let's stop the video now and have you guys try two examples. One is going to be simple. The second one is going to be a little bit more difficult, just like the two that we did together as a class. So pause the video now and then unpause when you are ready for the answers. Okay, here's our answer for the first one. Pretty straightforward. You'll notice that the magnesium carbonate dissociates in a 1-to-1 ratio. So if we know the concentration of the solution, then you know the concentration of each ion that's in it. In that case, it is 4.2 times 10 to the minus 6 molar. We set up our KSP and we multiply, getting 1.8 times 10 to the minus 11. The second equation here is slightly more complicated, as was the example we did as a class. You'll see here we are dealing with the aluminum chloride salt, which has a solution molarity of 3.8 times 10 to the minus 3. That means when this dissociates, my aluminum will have the same concentration as the solution molarity, but my chloride is going to have a molarity eventually that is 3 times that. So when I write my KSP, I know that my KSP is going to be this, with the chloride raised to the third power. And when I go to do the math, I have to remind myself that my chloride concentration is going to be 3 times that of my aluminum. So it's 3x. And of course, we're raising it to the third power here. So you'll notice I am going step by step. And eventually I wind up with a KSP that is equal to 5.6 times 10 to the minus 9. So the last segment of this video is going to go backwards from what we just did, where we were given the molar solubilities and we had to calculate KSP. Now we're going to be given KSP and we got to figure out the molarity of each ion. So if you look on your companion worksheet, here is the first question. It says, if the KSP of radium sulfate is 4.0 times 10 to the minus 11, then what is the molar solubility, or the molarity, of each ion in water? So what do we have to know? Well, we're giving you the dissociation equation here, so we don't have to write it, but we do have to write the equilibrium expression. So the equilibrium expression says KSP is going to be equal to concentration of radium times the concentration of a sulfate ion. And now we want to substitute what we know. Well, we know the KSP is 4.0 times 10 to the minus 11. And mathematically, we know we got that number by multiplying the radium concentration times the sulfate concentration. So we see when this dissociates, it is in a 1-to-1 ratio. So we're going to say x times x. So now we are just going to solve for x. So let's simplify what we got here. We have x squared here, 4.0 times 10 to the minus 11 equals x squared. I am now going to have to take the square root of each side. And if I take the square root of 4.0 times 10 to the minus 11, I wind up getting 6.0 times 10 to the minus 6. Now, what does that answer mean? Well, so that answer means the concentration of radium in solution is 6.0 times 10 to the minus 6 molar, and the concentration of sulfate would also be 6.0 times 10 to the minus 6 molar, because remember, they dissociate in a 1-to-1 ratio. So the second example is slightly more difficult than the first. So let's embark on how we solve this. First thing we're going to see is that we didn't get the dissociation equation, so we have to write it. That is PbCl2 in the presence of H2O is going to give me Pb plus 2 Cl minuses. So I know that the concentration of my chloride is going to be 2 times that of my lead in solution, and that's going to matter later. Let's write the equilibrium expression. Ksp is going to be equal to the concentration of Pb plus 2 times the concentration of chloride ion raised to the second power, because remember we have a coefficient of 2 here. Let's now set up our math problem. So we know our Ksp is equal to 1.6 times 10 to the minus 5, and we know that's going to be equal to, since we don't know these concentrations, and there's only one of these, it's going to be x, and in this case, we know that the concentration of chloride is going to be 2 times what x is, raised to the second power. So to simplify that, that is going to look like 1.6 times 10 to the minus 5 equals 2 squared is 4, x times x squared is x cubed, so it's going to get me 4x cubed here. We are now going to solve for x. So I have 1.6 times 10 to the minus 5 is equal to 4x cubed. So first thing I'm going to do is I'm going to divide by 4. And if I do that to one side, I got to go do it to the other. And that is going to give me an answer. Put in the calculator. That is going to give me 4.0 times 10 to the minus 6 is equal to x cubed. So now what we got to do is we have to solve for x. So in order to get rid of the cubed, I'm going to take the cube root of both sides. And that is going to get me the cube root. X is going to be equal to the cube root of 4.0 times 10 to the minus 6. And x is going to be equal to 1. X is going to be equal to 1.6 times 10 to the minus 2. Now, what does that mean? That is the actual concentration of the lead ion in solution. So I can say that the concentration of Pb plus 2 is equal to 1.6 times 10 to the minus 2. Mathematically, I know the concentration of my chloride ion has to be twice that of lead. So that's going to be equal to 2 times 1.6 times 10 to the minus 2. And that is going to give me a concentration of 3.2 times 10 to the minus 2. So my chloride ion is really this, and my lead is that. And that is how you solve that problem.
To practice this, we are going to embark on your KSP practice sheet in your plan sheet, which is a little bit of this and a little bit of that.
Make sure if you get stuck anywhere, you go revisit the video or your notes. And if you have any questions, please bring them to the Burning Questions segment tomorrow. So that's it for me, guys. It has been a pleasure to be with you. I will see you on the flip side. Peace out.
That's all, folks.